so much for having me at this awesome event. And I'm going to go into kind of a pretty deep application area. We've heard a lot of awesome technology that can apply broadly in many different areas. And I'm going to focus on one specific area in medical diagnosis that we're tackling at PathAI. Ooh, well, this slide's a bit off, but the story the slide is telling is that when a patient goes into a clinic, they'll come in with certain symptoms, and there's sort of a diagnostic odyssey where they have to go through a set number of steps. So typically a patient will go to a doctor because they're worried about something, and the doctor will then do some tests to find some clinical signs. And if they're also worried, kind of their diagnosis might then lead to another step, which might be radiology imaging. And the radiologists look at non-invasive imaging, which is pretty good, but it's not sort of cellular resolution. And if they're worried and have an impression that something bad might be going on, they'll order a tissue biopsy. And it's really that tissue biopsy that forms the definitive sort of ground truth diagnosis that will guide all future decisions. So if a patient undergoes a biopsy and the physician says it's benign, the patient has a clean bill of health and essentially won't require any treatment. But if the pathologist who looks at that biopsy specimen says this is a malignant cancer, that will start a whole cascade of treatments that are required to cure that cancer. So it's really one area of medicine diagnosis that we absolutely want to get right, because the pathologic diagnosis really informs all subsequent medical decisions. And we should be a little worried just because so much trust is given to the pathologic diagnosis, and sometimes complete trust can sort of be its own pathology, and we have to kind of look at that and think, if it's correct, it's great, but if it's a mistake, it can have huge consequences. So people have started looking carefully at this. So do mistakes happen in pathology? And it turns out they happen quite commonly. So the typical data type that a pathologist looks at is an image. So as we've seen in many areas, humans are good at image recognition, but they can make mistakes, and there can be variability across different humans based on sort of the different models people are using inside their own brains. So what this study showed that was published in the Journal of the American Medical Association about 2 years ago is they wanted to see what was the diagnostic concordance in the interpretation of breast biopsies. So they took a group of hundreds of pathologists across the country, and they asked them all to look at something like a few hundred cases. And what they found was an overall concordance rate of only about 75% across all biopsies, but only 48% for one of the most important diagnoses, which was atypia. And this is the data from this study where each column represents one patient sample, and the color in each column represents the proportion of pathologists that gave it a certain diagnosis. And you can see for every single patient, there's a huge range of possible diagnoses based on who the sample was sent to. So you would like, if you get a certain sample taken, you send it to the doctor, they're going to give you the same answer no matter what. But it turns out that's really not the case. And in many cases, we see a huge range of diagnoses from completely benign, here represented by the beige color, to completely malignant, represented by the orange or red color. And here's one example of a certain case. So this image was shown to 27 different pathologists, and a third of them said this is completely benign, clean bill of health. 13 of 27 said this is atypical, requires further intervention. And 5 of them said this is actually cancer. And we think computers can really be good at getting the perfect diagnosis every time and having it be a very standardized, reproducible process, particularly with recent advances in computer vision over the past couple years. And these set of 3 images are just showing these are 3 different diagnoses that were shown to this community of pathologists, and they saw quite a bit of variability in diagnostic practices. So there's clearly a sort of a health problem here to solve with computer vision, which is getting the right diagnosis to the right patients. There's also a major business problem affecting laboratories in America, where anatomic pathology labs are under intense financial pressures. They keep wanting to get more and more information out of each tissue specimen, but reimbursement rates are being cut significantly, whereas in the past couple years in pathology, they've cut a third. So pathologists are lowering a number in America as well as around the world. There are certain countries in Africa that have 0 pathologists in the entire country. So diagnostics, making diagnostics accurate in those countries is extremely difficult. So we have a major business case to want to get more accurate diagnoses per pathologist, as well as to be able to distribute these accurate diagnoses globally. So what is the actual visual task pathologists are dealing with on a daily basis? So a pathologist will sit down at their desk in the morning and have something like 500 glass slides, and each glass slide contains on the order of tens of thousands to hundreds of thousands of individual cells. And they're really responsible for giving the right diagnosis to every single cell in every single image. And this is really just an impossible task for a human to do as effectively as a computer for certain things, just simply because we're not able to look carefully at every single cell. So here's an example of one breast cancer lymph node biopsy. And this is what the pathologist sees as the first one, and the second one is what the computer sees, and where the color on the heat map represents the computer's interpretation of what it's looking at. And what you can see is the computer really focuses on several hotspots within this image. And then if we go into those hotspots in depth, we see that those in fact contain tiny little metastatic foci of cancer cells. So this is an example of artificial intelligence sort of painting every single pixel on this image, and then giving its opinion of whether that pixel contains cancer or doesn't. And that analysis can then guide the interpretation of the pathologist to then confirm, yes, that tiny little hotspot is in fact a tiny focus of metastatic cancer. And just to show you what people are doing today, both in America and around the world, and what we think they should be doing using solutions like those provided by PathAI, is represented in this slide. Whereas on the left, you see this glass slide where a pathologist with a microscope with no assistance of computer vision or machine learning sort of manually looks at high power or low power at kind of a haphazard subset of fields within the image, and then is required to summarize what they're looking at in an empty pathology report. And this is a very time-consuming task, as well as a task that's prone to error. A recent study showed for this application an accuracy rate of only 85%. And this gives low overall reproducibility. What we're doing is we provide pathologists with both the raw image, so they're still looking at the same raw data as they're used to, as well as the image processed by a deep learning system, which essentially identifies the areas of cancer and then enables the physician to focus on those areas. And we can auto-fill out a report based on the AI's interpretation of what it's looking at. And now the pathologist's job is really to correct or confirm the diagnosis provided by the AI system and then move on to the next case. So this can be a dramatically faster procedure. We've shown in our studies a significant increase in accuracy, where we can get the accuracy rate of human plus computer to less than 0.5, the error rate to less than 0.5%, with extremely high reproducibility because the AI system helps standardize diagnostic practices. And that's sort of an overview of our overall mission. And we see this as a very broad applicable technology across really all areas of diagnosis requiring microscopic imagery, which includes the types of images I showed, as well as different types of images stained with different biomarkers that can help guide treatment decisions. But overall, our mission is we use deep learning to build image recognition solutions for applications in pathology. And our solutions reduce errors, increase efficiency, and then seek to match the right patient to the right treatment. And overall, we aim to advance medicine with intelligent pathology. So thanks very much for your attention. And that's our overview on PathAI. And if you'd like to learn more about the company, please send me an email or talk after the session. So thank you.